Without further ado, Priya.
With me. Now, aging and oral health, that's the basis of my project. Do you think aging affects oral health? How many of you think it does affect? It does. And how do you think it affects you? Lose teeth, definitely, and lose gums, lose teeth, and we have dentures. Now, what happens when we are taking medications for other systemic blood pressure, diabetes? One of the common side effects is dry mouth, change of taste, because some of the taste buds just stop working because of the side effects of those medications. When we have dry mouth as we age, the bacterial buildup is very high in aging mouth. And that's where the whole cycle of tooth decay, gum loosening, everything sets in. Wear and tear is a part of aging. Not only the teeth, but the muscle mass, gum tissue, everything that leads to loose teeth, ill-fitting dentures, gum recession. And that's where the whole cycle of, thank you, just resorting to soft food, sugar-rich drinks, and that's where we end up eating something which we should not be eating at a higher frequency. Now, let's talk about the connection between the mouth and the body. Heart diseases, diabetes, grinding of teeth, I would say anemic individuals, they have pale gum teeth. Renal disorders, they are connected to loose teeth, early tooth loss, especially the diabetes, which is very significantly evidence-backed. If you have more blood sugar if you have higher blood sugar, the bacterial buildup is very high. The cycle sets in, it feeds the bacteria. The bacteria starts growing, it starts loosening our teeth. And that's where, again, we end up eating softer, sugar-rich food, and it just keeps deteriorating. Another aspect to that, so what happens when the oral diseases that have set in, they are not treated in time or not taken care in time? I would say they are not prevented in time or not nipped in the bud. The pain makes the whole process worse. We have poor eating habits. We have reduced self-confidence because of loosened teeth, crooked teeth, decayed teeth, and the bad breath that makes it worse. Complications of other systemic disorders and infections. So, after doing some background research and looking into other reports from OECD countries, it was found that why our seniors are not able to maintain a good oral health. Why there is poor oral health amongst our seniors? It's because with aging, there's a decline in their self-care ability. People with arthritis have a lesser strength. They can't hold the brush, they're not able to brush properly, oral hygiene measures, flossing, that becomes a challenge for them. Tooth decay and pain and infection sets in a cycle, leads to poor oral health. Long waiting lists at the dentist, it's forever. We have seen appointment for a dental decay and a root canal takes around 3 months waiting period by the time a person loses the tooth. So that's another challenge what we are facing in the regional area, especially our seniors. And the most important one, the financial limitation. None of the insurance is covering the dental treatment. We have very limited dental schemes for our seniors. We have some for our kids, but not for the seniors. So all the plethora of these factors, they are ending up poor health amongst our seniors. Now I have just a general question. Do you think poor oral health is having any impact, psychological? Do you think so? How do you think the psychological impact would be?
Well, the pain for a start to put you up.
Exactly, the pain at the start, you don't feel like eating anything, you don't feel like meeting people because of the bad breath or the crooked teeth. You are waiting for the appointment, it's not really happening. So, from the survey, National Oral Health Survey, it was found that 23% people between aged between 55 to 74 years old, reported that dental costs were the main barrier for them to seek any dental treatment. 1 in 5 people over 75 years old had a difficulty paying $200 bill. 20, sorry? Yes, and any dental treatment, as I have seen around here, doesn't cost less than $120 to start with, be it a decay, scaling, anything. And then 28% of 55 to 74-year-olds, they have stopped eating the food that they should be eating to fulfill the nutritional requirements and the taste, of course. And last, which is very shocking, that 25% of the people who are eligible for the public dental schemes, they don't have enough teeth to be taken care of. So when they go to dental, okay, you are eligible for the public dental scheme, but there's nothing in the mouth. It's taken forever in terms of appointments. So, sorry, stool? No, it's okay. I'll stand. I'll go to the side.
It's just the microphone if it's something.
Okay. I know. Sorry, it's the height. I was wearing heels but couldn't hear much. Okay. And, yeah, what I was saying. Oh, yeah. So 25% people who are eligible for public dental scheme, by the time they reach the dentist, the teeth were gone. And it has happened personally with some of my patients when I was practicing back in Malaysia, that they had appointment after 2 months, and they came with a little bit of wiggly tooth. Oh, we were supposed to treat it with root canal, but it's better you extract it now. So that's the thing that is happening over and over, especially in the regional areas. So another quick statistics about the missing teeth. There are many factors that were contributing to that. If we look into the gender, doesn't have not much significant impact on the amount of missing teeth, but remote location, geography has a very significant impact. People living in remote or very remote regions had 12 missing teeth per mouth compared to the ones who are living in the cities, major cities, definitely because of higher availability of dental resources. Health insurance had a significant impact. Individuals having no health insurance had significantly high missing teeth in their mouth. Those eligible for public dental care, the one who were eligible had more missing teeth again than who were not, probably because of the socioeconomic and access to the services. By the time their turn came, the teeth were lost. And household income had a huge impact as well. Those individuals having more than 140K annual income had significantly less missing teeth in their mouth compared to the ones who had less than 30K. So that's a quick stats, and it was derived from AIHW Australia in 2016. Now, latest report by Aged Care Insight, it was given by President of Australian Dental Association, that patients with dementia, inside the aged care, patients with dementia and those with arthritic hands found it very challenging to maintain the everyday oral hygiene. Overstretched staff in the aged care, they were not trained properly for maintaining the oral health of the residents. They couldn't deliver the appropriate oral health care. And what happened, by the time they did this study, at the end of the study, they found that there was very deteriorated oral health of the residents. To name a few, broken dentures, long-lasting vestibular ulcers inside the gums. They were not able to eat. They were just relying on the liquid foods. So after getting to know about all that, our team, sorry, I'm trying to figure out this software. Our team of researchers at UTAS, Dr. Tony and Dr. Ha, with the help of my supervisors, we came up and we thought, why not to start a community-based strategy, a group strategy. When our seniors are independently dwelling in their households, they still can take care, they are physically active, they can still maintain their oral health. Why not to start a group activity? It's still in the pilot state, we are still in the process of testing it, so that we can inculcate a bit of oral health awareness. We can tell them about how we can access these services, what are the dental schemes available. So I'll just go towards a bit of the design of our study. So we are trying to take advantage of a group effect. When we all come together, sit together, we'll talk about our concerns. Probably we'll be able to share some concerns which can be taken care of by a bit of a knowledge, or by the way they are taking care of their oral health, which the other person is not aware of. Availability of other oral health care resources that we are not aware of, which are run by the state dental schemes. Some coupons for our seniors, which are not advertised well, and probably we can direct them there. So about the type of food that should be consumed, the preventative measures that we can take every day to address these conditions like dry mouth, having loosened gums, taste buds issue. These are the things which we can manage while talking to each other and just running an awareness program. So the study would go like this. We'll try to recruit the interested participants from the already running community groups. Once they are ready to participate, then we'll get some written consent for them after telling them about the study. In the first meeting, we'll try to identify the type or the concern of the problem that they're having. It could be a very small one. It could be a small one, maybe brushing, issues in brushing, flossing, dry mouth, taste issues, some long-lasting ulcer. After identifying that, we'll do the assessment. Just by discussion, we'll just assess the oral health care practices, what is the oral health behavior at that point of time. After that meeting, we'll be running some 30 minutes long workshop every fortnight, and we'll try to go through those concerns over and over again. We'll discuss that, we'll try to address them based on available resources, referral, whatever is available at that point of time. And we'll be doing this assessment every fortnightly for 30 minutes on every session. At the end of the study, we'll again go back, assess the concerns. Are they happy with this strategy? Are they good to go with this type of program? Is there any change in their oral health care behavior, practices, or their concerns? And that's where we'll be producing a report. So that's the whole idea behind the group strategy and the community program that we are intending to run. So that's it. And do you have any questions? Questions in the end. Yeah, sorry. Thank you very much.
Hi. So my name is Eric, and I'm a PhD student at the Australian Maritime College. And the work I'm looking at is basically evaluating the effect that different mooring systems have on the hydrodynamic performance and the survivability for offshore wave energy converters. So I thought what we might do to start with is put the wave energy industry into a bit of context, and we would start to have a bit of a look at what the opportunities are with wave energy, because there is an amazing opportunity that we're not taking advantage of, but we should be, or we could be. So basically what I have here on the board is a picture which depicts the amount of energy that's around the Australian coastline. Now the CSIRO did a very big study a couple of years ago, and what they found is if you take the 25-metre water depth from Geraldton, which is about halfway up the West Australian coast, thank you, all the way around to the bottom of Tasmania, there is somewhat around 1,300 terawatt hours of energy available per year. That is 5 times the amount of energy that we currently use in the entire country at the moment. There is an immense amount of power out there. Hydro Tasmania, they make about 9 terawatts of power as it currently is. So that's an amazing opportunity to help us fix this clean energy issue that we have. Now when you think about it, that's only the 25-metre water depth area. If you move into even deeper water, let's say 50 metres or to 100 metres, the power profile increases proportionally, and there is a lot of opportunity. So what are the risks and what are the challenges? Well, first thing, the ocean environment is generally pretty calm. Okay, you might have 1.5 to maybe 3 metre waves, a bit of wind, a little bit of chop, nothing that's not unreasonable to manage. But then, every now and then, we have these enormous storms with gargantuous waves, immense energy, and the actual devices can be destroyed by wave loading and wave impacts during these big storms. And then you've got risks with, well, how do you actually build one of these machines, because they are very big, much larger than the size of the room that we're in, how do you move them across the ocean? How do you design the moorings so that they stay in position when there are these big storms? And how do you avoid the kind of catastrophes from happening that you can see at the bottom here? Now, these were all real devices in Australia, except for the very far one on the left-hand side, which is a tidal turbine, and that was in Canada. So this is what we're trying to avoid. And then we need to look at what the effect is in the environment. Now, there's been a whole lot of different environmental impacts for different offshore structures. This is just one example for a tidal turbine that was in Canada. It's a little bit of humour. Now, when we're looking at wave energy, there's not, from my understanding, now I'm not an environmental assessor or anything like that, so I can only sort of talk about what I've read. There's not a huge risk involved with wave energy converters. This is largely because the machines, they don't move very fast. There's not a lot of turning parts. They're very static in motion as it is. But there are a couple of things that we need to evaluate. The first thing is how does taking the waves out of the environment affect the sediments that are behind it? Because there are a lot of organisms that feed on the grasses and that live in those soils. And if you take away all the energy from the waves, you absolutely are going to change the beaches, the coastlines, and all the sediments below. So that's one thing we need to look at. Another thing is the moorings can absolutely damage the seafloor. So there are big chain moorings called catenaries that we use in the offshore oil and gas industry, and what happens is, as the device will heave upwards or surge backwards, the chain will be picked up off the seafloor and will be sat back down, and as it picks up and puts down, that can very well damage the floor. So understanding what those effects are with the moorings is really quite important. And there are a whole lot of other concerns about fish and bits and pieces. But one of the things we need to do is actually put these devices into the water so we can realistically evaluate what's actually going on. But it's not all bad, because when you think about it, these things not moving too much are very much like artificial reefs. And this is what they're finding all around the world. These big structures, they get covered in barnacles and they provide homes and bits and pieces for animals to live. And also, there's a very large risk with collisions. What we don't want are boats going into those regions to crash into these devices, because there's very powerful subsea cables and there's a lot of issues. And what that means is there are exclusion zones which will end up going around the outside of wave energy converters, which at the same time will act as like marine refuges, because we can't have trawlers going through those particular areas. We won't want people going into them to try and avoid the risks that are associated with it. So there's a bit of a risk, but at the same time, there are quite a few benefits that should be evaluated. Oh, wrong way. Okie dokie. So what I thought we would do is step through the 4 basic types of wave energy converters. Now, the first type is called an oscillating water column, which is this one here on the side. This is the same type of device that's on King Island. So you guys would have heard there is a wave energy converter that was built here in Launceston and has recently been installed on King Island. That's this device right here. And what it is a big concrete structure that has a big hollow section on the inside of it. And when the waves interact with the outside, the water level on the inside fluctuates up and down. And as that water fluctuates, the air that's inside the chamber gets pushed over a turbine, which is where the power comes from. This is the type of device that I'm working on in my research, and we'll go into a bit more detail about its working processes afterwards. And then we've got a whole different type of device, which is called a wave-activated body. Now, this is like a big floating buoy. Some of them are on the surface, some of them are under the water, some of them are actually big hinges with like a big floating cylinder that's attached to the sea floor. And what we're trying to do here is convert the hydrodynamic energy that's in the waves into kinetic energy of the structure. So we're trying to actively make these things move, and then we're trying to convert those motions into electricity. Okay, and there are some challenges. A couple of the challenges with these devices is the fact that there are a lot of moving parts below the water, which means there's going to be a lot of corrosion problems, there's going to be a lot of maintenance problems, and it's not like we can just send people out there to fix something up in the subsea environment. We need specialist divers, which becomes very expensive. So there's a lot of work in wave-activated bodies, but there are a lot of challenges associated too. Then we have a device called an overtopping device. And this is a big floating structure with a big reservoir above the mean water level. And the way it works is the waves will run up the side of the device and flow into the big reservoir, and the gravitational potential energy that's in that water above the mean sea level will trickle through a turbine and make power. These types of devices had a lot of promise maybe 20 years ago, but there's not a lot of research being done on them, and I'm not exactly sure why. And lastly, we have the new kids on the block. These are called pressure differential devices. And the best way to imagine them is it's kind of like a hot water bottle. It's a big rubber membrane that's full of air, and as the waves travel over the top, the difference in the pressure because of the weight of the waves presses the air out of the membrane and over a turbine. And then the wave passes and that air goes backwards back into the chamber. Now these devices are being developed very rapidly. It looks like good technology to me, but there are some challenges with the maintenance because they're always on the seafloor. So they're the four big ones. Now these are a couple of real devices that use those different principles that are actually out there at the moment. On the top left we have the wave swell energy device, which is on King Island. That device is actually there right now. You can see it is pretty close to the beach, right? It's right in eyesight. Then we have a floating pressure differential device that's next to it. And then we have another type of oscillating water column at the top. On the top right-hand side, we have a wave-activated buoy. This is a point absorber. And so this device basically oscillates with the waves, and there are a lot of mechanisms on the inside of it that convert those motions into power. And down the bottom here on the left, we have a pitching plate. This is one of those hinging wave-activated bodies that I described before. These devices produce a lot of power, the wave-activated bodies, but there's the challenges with it. And then we've got a bit more of a creative idea. The device at the bottom in the middle, the yellow guy, this is a huge big pendulum. What it is a box barge that was designed to oscillate, and then you've got a structure with a big concrete block that swings in that line, and they're trying to convert those rotations into electricity. Okay, this was actually built, it's a company in Melbourne that designed it, and it was in Wales being tested. Okay, interesting idea, lots of moving parts. I think probably lots of things that could go wrong, especially in 20 years' time with all that stuff that the sea has to offer. So, what am I doing? Rightio. Now this is the type of wave energy converter that I'm actively testing at the Maritime College. It's an oscillating water column, has the same working principle to the device on King Island, but there's some very big differences. The first is the King Island device is a 600-tonne piece of concrete that sits on the seafloor. It doesn't move. This device is designed to float out there in the ocean, and it's supposed to be much further offshore where we can access a lot more energy. And what you can see is there is a bit of a hole at the front for the waves to go in, and then the inside of the chamber is completely empty. And to visualise what's going on with the device, I have set up a series of computational fluid dynamics simulations to illustrate how those motions work. So we can see the wave comes into the front of the device, and the wave runs up the front, creating a very large amount of hydrostatic pressure from the waves, and some of that energy is pushed into the chamber, and the water is oscillating up and down, kind of like a piston inside of a car. And that's where the power comes from. Now, if we have a look at what the air is doing on the inside of the chamber, what we can see in this animation are a series of little vectors, which are little arrows that point the direction that the fluid is moving, and the colour shows the velocity that the air is moving at. And what we can see is when the water level rises, there is a big jet of high volume, high velocity air shooting out of the orifice at the top, and then when the water level comes in, the air is drawn back into the chamber. Now, in the experiments that we do at the Maritime College, the models are about, well, this model is about a cubic metre in size. it is too small to actually have a turbine on the top of it. So what we're doing is we simulate the resistance for a turbine with the size of that orifice. And as this device is built into a bigger scale and further tested, there'll be, like a 3D printed turbine that will be used, so we can actually measure what the electricity is being produced, which is nice and easy way of doing it. Now, that's great. We have a device that works. We know how it works. We've tested it to death, but it doesn't matter if it won't survive the ocean waves. So what I've done in my PhD is found the balance between how does it work in the operational condition and will it survive. And to test whether it survives, what I've done is made, I designed some waves to make some of the worst possible conditions that you can expect from a wave energy converter. Now, this wave that we're looking at, this video here will show it in a slower speed because it's travelling very fast. You can see the wave is about the height of the device. Just as it approaches, it sets up, it starts to break, and then, blam, slams into the front of it. And what we're actually doing is, I have, not in this video, but in a whole bunch of different experiments, placed a bunch of different pressure sensors along the front of the device, and I have load cells in the moorings. So what we can do is measure what those slamming pressures actually are and what the mooring responses are in terms of tension and loads. And then with the computational fluid dynamics simulations that I had showed you before, we can simulate those exact conditions and then collect the full pressure field across the whole device. Because what this means is we now will have a detailed understanding of, well, what are the actual design criteria for these kind of devices? What are the loads that are actually placed onto these devices, and what do we need to do to make sure that they don't end up being washed up on the beach or the subject of somebody else's presentation next year, which is what we don't really want to happen. So that's the work that I do. Now, what's the future? Well, there's still quite a lot of information that we need to understand, a lot to work on, but we should still continue to develop these technologies because there is an enormous amount of energy that's available for us out there. Yes, there are some technical challenges, and different universities around the world, particularly us at the Maritime College, are working on overcoming a lot of these problems to make this something that's going to be a real reality. And in my experience and thinking, the way to do this is we need to find the balance between the performance of the device, the survivability of the device, the economics of the device, and making sure that we're not having a negative effect on the environment. So that's the nature of my presentation, and I look forward to some questions after Kate has presented. Yeah.
Thank you, Eric. Well, we started in the mouth, we've been to sea, and now Kate Edwards is going to take us a little bit lower down. She's investigating the connection between exercise-induced gut damage, estrogen, and the gut microbiome, and how it may impact on female health and performance. She has a Master of Science in Sport and Exercise Nutrition at the University of Westminster in London, and this is what she's working on.
Thank you. Thank you. In the late 1970s, a marathon runner named Bill Rogers, who had won both the Boston and New York marathons twice, commented that more races are won or lost in the porta toilets than they are at the dinner table. Now, there must be a few runners in this room, because every time I mention that comment, there's always a bit of a nod of recognition that no matter how good your training and how good your diet, a race can be just so easily derailed by a dodgy tummy. Now, since the 1970s, a lot of research has been done on how to manage those symptoms and how to mitigate potential disasters on race day. But more recently, we've come to understand that symptoms are not the end of the story. That, in fact, the gut can experience physiological and structural changes that can affect both its function and its integrity. So when I talk about gut damage, what am I talking about, and how does it happen? Well, the gut lining has many folds, but it is only one cell thick. And the cells are held together by proteins, and they're also protected by a mucus layer, which protects our insides from what's coming through the intestinal system. But during exercise, two things happen. Firstly, your body increases sympathetic nervous activity, and your sympathetic system is your fight or your flight system. And that decreases parasympathetic activity, which is your rest and digest system. So during exercise, your body gets ready for action by decreasing functionality to your gut. Secondly, blood is redistributed to the working muscles because that's where you need it, and it's redistributed to your lungs and to your heart. But remembering that blood carries all the good stuff like oxygen and nutrients, then a reduction in blood flow can result in an increasingly acidic environment in the gut, but also hypoxic or low oxygen conditions. And that can lead to gut damage. And we call this reduction in blood flow with the combination of low oxygen ischemia, gut ischemia. So once the cells are damaged, they're no longer held tightly together by proteins, and the gut barrier becomes permeable. It allows things that we would normally keep out of our circulation into our bodies, and that can include food particles and pathogens and bacteria. Things can move the other way. You can also lose blood and nutrients into your intestinal cavity. But exercise is not the only situation in which reduced blood flow can cause gut damage. This also happens in trauma cases and in some cardiovascular and hepatic conditions where gut ischemia results in bacteria getting into your bloodstream and you get an inflammatory response. And it's a leading cause of morbidity and mortality in these conditions. And we can actually measure gut damage using a particular protein called intestinal fatty acid binding protein, or IFAB for short. And we can measure that in our blood. Trauma, exercise, what's one got to do with the other? Well, these clinical issues are relevant because just exercising at 70% of our maximal capacity can result in a reduction of 80% blood flow to our gut. And that's equivalent to what we see in some trauma cases. So the first study in my PhD actually investigated the effects of increasing intensity on this damage to our gut, and it looked at IFAB in blood samples. And what we saw was that at low intensity, at just 40% of our maximal capacity, no evidence of damage. At 60%, it was quite individually variable. Some people showed damage, some people did not. But at 80% of our maximal capacity, we actually saw quite a bit of damage. People are far more susceptible to this gut damage when they're working at higher intensities. Now, before you go and cancel your gym memberships or stop running or walking or whatever you're doing, it is highly unlikely that this acute and very specific damage is a problem to most people, especially if you're training correctly and you're recovering properly. But it also might even be helpful in developing our immune systems because we get that immune response when we get the damage. But for athletes who are regularly training at high intensities and who are not taking a lot of rest, who are training multiple times a day and doing extreme exercise like ultramarathons, then we may end up with damage that causes problems with nutrient absorption. It interferes with their training adaptations, it can impact their recovery, and it increases their risk of illness and injury. So in 2017, Costa et al. Developed this model of exercise-induced gastrointestinal syndrome. And it encompasses the primary factors that we know about, so the circulatory issues, the redistribution of blood, and the sympathetic increases, which cause the secondary outcomes, so the ischemia, the damage, inflammation, and the exacerbating factors. And you'll notice that sex is an intrinsic exacerbating factor. But despite acknowledging this, there are no sex-specific guidelines addressing this problem. And the underlying evidence base for this model is overwhelmingly from males. So what evidence do we have that sex might be a factor in this exercise-induced gut problem? Well, let's go back to our trauma patients. It's been observed that females who are in this situation with trauma and gut ischemia tolerate that better than males. and it's believed that this may be due to female sex hormones. So the hormone estrogen might actually help protect the mucosal barrier by increasing bicarbonate secretion when the environment becomes very acidic. Estrogen can also upregulate the proteins that hold the cells together, so it helps with the permeability problem. And it also might function in maintaining blood flow. Estrogen can also act centrally on our nervous system, so it can increase our parasympathetic system, that rest and digest, maintaining functionality in our gut. Progesterone, on the other hand, another female sex hormone, can actually act in the opposing direction and increase our sympathetic nervous system. So it seems like higher estrogen is good for protecting us from exercise-induced gut damage, and that progesterone may exacerbate it. But as always, it's not that simple, because female hormones fluctuate during the menstrual cycle. An average cycle is often represented as 28 days, but it can last anywhere from 21 to 35, and often even more or less than that. But essentially, day one of the cycle is the onset of bleeding, and estrogen and progesterone are both low. Estrogen will increase twice over a cycle, first just prior to ovulation, and then in the latter stages of the cycle, whereas progesterone will have its peak only once. And from studies conducted in animals, we actually see that in mice, when they're sort of subjected to ischemic gut damage, that fluctuates during their cycle. So it's quite possible that we are susceptible to gut damage at different times of our cycle as humans as well. This has never been tested though. So part of my PhD is trying to answer that question. A second factor in differences in gut damage is the microbiota, and I am by no means claiming that this is scientifically accurate. It is what you get when you Google microbiota. We are only just beginning to understand the role that the gut microbiome plays in gastrointestinal disorders such as inflammatory bowel disease. But there is evidence that certain species of bacteria can actually enhance that intestinal barrier function. And there's what we term the estrobolome. And that's a really lovely word that encompasses all of the genes in this bacteria that can actually metabolize estrogens. They contain enzymes that make estrogen available for us to use. So we have really strong links, not just between estrogen and gut integrity and the microbiome and gut integrity, but also between estrogen and the microbiome. But why does all of this matter? Well, I'm sure many of you have spent time watching the Olympics over the last few weeks, and you'll be watching the Paralympics in the next few days when they start. Taking 1 second off your 100-metre time can mean the difference between winning Olympic gold and not even making the final. Taking just 2 seconds per kilometre off your marathon time, just 1.5 minutes over the course of more than 2 hours, can make the difference between being on the podium or not. But women have only been allowed to run in the marathon since 1972. It wasn't even an Olympic sport for females until 1984. That's my lifetime. That's 90 years after the men. But we only have to look at the improvements in women's marathon times to see that once women have access to sport and access to coaching and access to guidance, that we are perfectly capable of producing outstanding performances. For female athletes, whether recreational or elite, there are no sex-specific guidelines for training and nutrition that take into account female physiology and the fluctuations of hormones. That includes lifespan hormones such as puberty, pregnancy, menopause, nor does it take into account things like menstrual irregularities or hormonal contraceptive use. There is a fundamental inequity in the quality and volume of research that addresses female athletes. It is unfair that females, in many cases, already having to overcome barriers to sport that don't exist for young males, are not afforded the same robust, evidence-based recommendations that are available for their peers. And as a result, female athletes may not be realising their full athletic potential. It may even be harming their health. So how can knowing about the influence of the menstrual cycle on gut damage help our performance? Well, traditional methods of training, ironically, are periodised. And periodisation is, most basically, it's about increasing intensity and or volume through cycles to reach your peak performance. So the shortest cycle there is the microcycle, which is made up of daily sessions. They move on to mesocycles, which can be about a month, which move on to a macrocycle, which can be the length of about a year, or if you're an Olympian, a 4-year cycle for them. But it's these microcycles and mesocycles that I'm most particularly interested in. Within the microcycles, say within the course of a week, there will be a mix of training sessions, both high intensity and low intensity. But if there are particular phases of the menstrual cycle where an athlete may be more or less susceptible to gut damage, then we need recommendations and suggestions on how we can manage those training sessions and appropriate recovery, and maybe consider how there may be different ways of approaching periodisation that we can actually get optimum benefit out of fluctuating hormone changes. Understanding the menstrual cycle, not only just by scientists, but by every individual, and how to train appropriately may have real impact on athletic performance. It also will impact on female health, on a female's ability to exercise just on a day-to-day or a week-to-week basis, and whether or not she is going to become a healthy, lifelong exerciser. There has been and continues to be some great work in this field, and my PhD is just a very small part of this. But I hope that my research will directly influence the recommendations we make to female athletes for their training, their racing and nutrition, to optimise their performance and their health, but also to help our younger generations coming through to understand their bodies and understand those changes and help them on their journey to becoming athletes. Thank you.
Do we have any questions from the people watching on screen? Not at this stage. John.
I'd like to ask Priya, how often does someone with dentures need to have the dentures replaced to sort of keep up with the bone loss that occurs?
So if someone is having a systemic disorder underlying like diabetes or other immunocompromised disorder, we generally call back the patient around at least once in 3 years to check the bone height. And if it's losing out or the denture is rocking, if the patient complains the denture is rocking, we tend to replace. And it's mostly the lower bone that goes off, not the upper bone. And that's where it's mainly once in 3 years, unless the person is having a systemic disorder or if the denture is broken.
Thank you.
If I may ask, sorry, would you mind if we had our speakers join you up on the stage?
Yes, come up.
I'll run around with a microphone and...
That's a much better idea.
Yeah.
Eric?
Your hands seem to be waving further that way.
Eric, I've got the microphone. Could I ask Kate Edwards a question? And I'd like to congratulate all the presenters. It's very excellent. You've talked about how the menstrual cycle affects ability to exercise, or might well do. To what extent does the fact of exercising affect the menstrual cycle?
That's a great question, and it does a lot. They're both very much interconnected. So one of the biggest effects from the menstrual cycle on exercise is that if an athlete has low energy availability, one of the first things the body will do would be to slow down that reproductive cycle. So you can, as an athlete, lose that menstrual cycle if you have low energy availability. And once that happens, then that can really affect your performance as an athlete, detrimentally affect your performance. Does that answer the question? Yep.
It's a question for Eric. You mentioned that a whole lot of people around the world are using different types of devices. You also mentioned there's a whole lot of research going on around the world. I have two questions. One is, what seems to be the, if you like, the flavour of the time as to which type of device is most worked on, most interested in, and so on? And the second is, you're doing some work on your wave oscillation column. Presumably other people are doing work on it as well. What are you doing that's different to what's already happening?
Okay, good question. Right, so one of the fundamental problems that the wave energy industry has is the fact that nobody across the world are trying to condense the information into a smaller pool. So when you look at the wind turbine industry, 30 years ago there were lots of different ideas, and all of that has converged to what we now know as what the wind turbine looks like. But that hasn't happened in wave energy yet, which is a problem because it seems to be there's a lot of people saying, wave-activated buoys are the way to go, or oscillating water columns are, and then somebody else will come up with a new idea next year, and then we can add to the flavour of what's going on. So it's kind of hard to answer that question because at AMC, for example, we do a lot of work with oscillating water columns, and so we like OWCs. But other universities have their speciality, and they will actively promote their topic as much as they possibly can. I think at the end of the day, it's going to come down to the economics. So which device is going to be the cheapest to produce and have the least amount of ongoing expenses over time? Because that's the biggest problem with the wave energy thing at the moment, is the cost of the electricity is higher than what it is for wind. And that means when people go to invest in it, they have more incentive to invest in wind because they're going to get a better return than the possibility of not getting a return at all in wave energy. So we're not quite there yet, but that's where we're at. Now, for your second question, what I'm doing differently with my technology is I'm looking at the effect that the external part of the geometry has on the performance. So historically, everybody has, looking in OWCs, or the oscillating water columns, has looked at how the geometry of the chamber itself affects performance. And what I'm doing is looking more holistically across the board. I'm saying you need to design the internal part of the chamber, and you need to design the external part of the chamber, which is going to make it float and control the dynamic motions and the responses. And at the same time, you have to also consider what the moorings are doing. So my work is more holistic rather than very targeted and focused, because we can do a huge amount of work on an individual thing, but until you look at the bigger picture, it doesn't fit together as a bit of a puzzle, if that makes sense. Yeah. Does that answer your question?
Thank you.
So, Eric, we've got these big wind farms out. I'm from the UK, and we've got them all around the UK. Why can't you tie your wave machines into those structures for stability?
Yeah, I think that's where we're likely to see wave energy actually happening. What I would like to see, especially in the UK, is in between those big fields of wind turbines, having wave in between, for two reasons. One, because there are definitely waves that are in there, but the really expensive part of the wave energy is the subsea cabling from the field to land. It's very expensive, it's prone to fail, and if we start working with the offshore wind industry, we can take advantage of the infrastructure that they've already put into place. Yeah, and so it kind of makes sense to concentrate that in, because it also means that we have a smaller footprint of impact on the environment, because they've already done a lot of the work with like what the impacts are going to be from the wind turbines. Yep, so that's what I think we should do. But what's limiting at the moment is we don't have a particular technology that's well enough defined yet to justify putting them en masse. We're lucky in Tasmania that the device they have on King Island it's a very good step forward. Once that's commissioned and it's working and it's producing power, hopefully we'll see that technology starting to be rolled out into breakwaters and into other coastal structures, and that will give more confidence to sort of push further into other technology. So we're not quite ready for it yet, but that's where we should be looking, I think.
Thank you. Kate, I'd like to ask you whether you think, or whether your study will take into its scope, the possibility of a young female athlete's ability to reproduce later on, because when she loses her period, etc., what is that going to mean in the future for that young woman? Because we know there are a lot of problems now with, people having babies later on.
Yeah, no, that's a really great question. So my research isn't taking that into account at the moment. That's part of probably a broader conversation to have. The world of sport is becoming far more attuned to female-specific issues, particularly along the lines of reproduction later. And as athletes go through their careers and they want to have children, how do we best support those athletes to make sure that that is possible? So we're understanding, and that goes a little bit back to your question previously, about how exercise can affect the menstrual cycle, and is ensuring that our athletes are supported, that we do have these guidelines and we do have these recommendations that make sure athletes are getting what they need to make sure that they're healthy, so that, as they get through their careers and they want to have children, there is no problem with that. There's a couple of really good books out at the moment. One of them is called No Period, Now What? And it's focused particularly on athletes who have lost their period during their training session and now want to get that back and how they can do it. So that conversation is definitely happening, slightly outside of my PhD, but yeah, it's happening.
Well, thank you.
Priya, how are you going about obtaining subjects for your study?
So we are still in the testing stage, and I have sent out letters to some community groups waiting for their reply. So the idea is to piggyback already running community groups. So they're already joining the program, and then we get in, and so we're in the process of, I've sent out letters. When I get the response, I'll get back to them, recruit them, get a consent, and that's where it kicks in.
Well, we'll just bring this very brightening session to a close. It's our habit to give our speakers a certificate to remind them that they were here, to hang on their wall. So, Kate?
Thank you very much.
Priya?
Thank you.
And Eric? Thank you. And also to lumber you with some of the Society's publications, which we're delighted to do. Everybody gets a prize.
Thank you.
Thank you very much for what you've... Would you join me in thanking our speakers for what they've done?